Great. So, thanks again, the organizers, for putting together this wonderful events. And thanks also for everybody who is still staying here. And my name is Zhenyu Liao, and I'm now working at Huazhong University of Science and Technology in China. And so this hour, in the next hour or so, I'll be talking about um, um, a lot of existing results. We try to putting them together, and it's based on a review paper that's so this one that is written very recently with Michael Mahoney. So I think I can skip this slide because it's just an argument to say that we have a lot of data and to align notations as well. So we have data vectors living in dimension P, we have N of them, and we have a large machine learning model, have, of size D, for example, of D parameters. And we are working in the region where they're all large, and working this region is, pretty different from standard region of statistics or classical statistical learning theory. And the random matrix theory, provides us some tool to understand what's happening. And I'll be specifically talking about the model of neural nets and try to present a unified framework on how to compute things in this region with, random matrix techniques. And here will be my plan. And I will be starting with, the unified framework. So how can we adapt existing results in random matrix theory to understand, for example, nonlinear, shallow or deep neural nets? And what are the challenges and what is the way to conquer these challenges? And then I will be, showing 3 examples. We're starting with the easiest one of linear least squares. So the model is linear and we don't have any depth. So it's a 1-layer thing. And we try to already apply the proposed framework to compute this and to show it's very different from existing results that people have been playing around in statistical learning theory for decades. And then we go beyond that to argue that we can do basically the same thing for a nonlinear model, a shallow nonlinear model. And we finally do some and go even beyond that to do some very preliminary results on deep neural nets. And let's do the first part. Okay. So in general, this is a slide that I try to summarize what is our objective of interest. So we may have a model, okay, random model in that's denoted by this M and some phi, x, and theta. So x is my data matrix that's in general random, and theta is my matrix of parameters that's also random. And the phi here is some nonlinear functions, just as described in Roland's talk. And the key is the object of interest is we want to understand the behavior of this nonlinear random model, but we only care about some, so its behavior, but measured by some specific function, or call this some performance matrix is denoted this function F. So it's going to mapping my nonlinear model that's in general matrix, but to some scalar. For example, in applications, we care about the classification error rate of my neural network. So it's going to give us a number. And that's the performance matrix F I'm talking about. Okay. So to understand this, we have a few technical challenges. So for example, the first thing is everything's living in high dimension. So in general, we kind of feel it's going to be very difficult to compute all these quantities. So my data are large random matrices. My parameter theta starts at random initialization is still a random matrix, but then we run gradient descent, so it's going to be very complicated, highly correlated, etc. Okay. And the second thing is, in general, due to the structure of gradient descent, etc., we care about the eigenvalue behavior, not only eigenvalues, but also eigenvectors of such nonlinear random matrix models. And the last technical challenges due to the entry-wise nonlinearity. Okay. And The good news is they can be resolved, and the idea is somehow intuitive. Okay, the first technical challenges of high dimensionality is in fact some kind of blessing. Okay, if you have large random matrices and this large linear nonlinear random matrices are passing to some performance matrix or observed through some function f to get some scalar random variable, you hope that there's a lot of randomness in the large matrices. Once compressed, we have a kind of central limit theorem kind of thing, or law of large number kind of thing, and they have strong concentration. Okay, so the quantity we care about, the f applied to the nonlinear model, will concentrate around the expectation, and we only need to understand the expectation. That's the first thing. The second thing is, when we care about eigenfunctions, fortunately, there is a very systematic way to compute all type of eigenfunctions of such random matrices. It's called deterministic equivalence for resorbents. And you play with the complex analyze a little bit, and you can basically get a lot of involved forms of eigenfunctions. I may need to skip a part of this. It's not going to be our focus today. And the last thing is pretty crucial as well. So you have entry-wise nonlinearity, and the good chances you can perform, depending on different regions, you can perform high-dimensional linearizations of nonlinear models. Okay, so even you are working with entry-wise nonlinearity, just as Roland mentioned. So essentially, it will become some kind of linear, and since we understand the linear thing, we can still proceed and understand the nonlinear model. So that's going to be the whole picture. And this is the proposed only one thing. If you want to take one message away, that would be this. So the idea of high dimensional equivalence. So we have some nonlinear random matrix model that depends on some random matrix, having some distribution, and also some entry-wise, nonlinear function is phi, and is observed through some scalar functions that is mapping, that's eaten some matrix, and output a scalar, so just like the classification error rate of your neural nets. And if we care about this, then it is possible via what I'm proposing in my previous slide to find its high dimensional equivalent, another model that is much easier to determine and capture exactly what's happening of your, previous nonlinear random matrix model, but observes through this function f. Okay, so there exists a way that exists this high dimensional equivalence, and the whole object of my talk today is going to find such high dimensional equivalent for different kind of models, for linear least squares, for shallow neural nets, and for deep neural nets. Okay, and this is just a notation. Okay, as long as we can find such high dimensional equivalent, and it is equivalent in the sense if you measure by some observation scalar function f, then we're happy because we know this equivalent, we can study this, and we can optimize this to get to understand and even optimize the performance and the design of my neural nets. Okay, and a few different special cases of this generic high dimensional equivalence will lead to a lot of things already existing in the literature. So if we don't have such entry-wise nonlinearity, this is just the standard deterministic equivalent in the context of random matrix theory. So you have a linear random matrix model. It is observed through some scalar observation. For example, care about its linear eigenvalue statistics or the whole eigenvalue distribution. You can always find a deterministic model that captures that behavior. So it's the idea of deterministic equivalence. And that's the second idea if you care about generic eigenfunctions. I'm going to skip that. And if things get more complicated and your model is nonlinear, then depending on whether you're in one of the two regions, you're being the law of large number region or the central limit theorem region, you can linearize your nonlinear model in different ways. and to get something called a linear equivalent, okay? And if you have your linear equivalent, you just work as, again, back to the deterministic equivalent thing and work just as if you're working with a linear model, a random matrix model. So all this together will help you have a way to characterize and understand those behavior of nonlinear random matrices, okay? And in the following few slides, I will try to, giving examples and illustrations of why this idea works, okay? So the first is a pretty simple illustration on this concentration idea, okay? We're not even playing with random matrices, just high-dimensional random vector, okay? We have two independent random vector. One is called X, it's of dimension n, and another is Y, it's also of dimension n. They are just of having ID entries of zero, mean, and univariance, okay? Then, if we consider the one-dimensional case, we have some kind of, Gaussian shape behavior, in the sense that each realization of your random variable will somehow concentrate around its mean, okay? If we are of mean 0, then you have a histogram that somehow concentrate around the value of 0, okay? Very natural. This can be proved, there are a lot of concentration inequalities, etc. However, in the multi-dimension case, in the high-dimensional case, you have large-dimensional random vector. We do the following calculation, okay? We try to understand whether it's a high-dimensional random vector will concentrate around its expectation. In this case, it's a vector of 0, okay? It's of a dimension n, so it's a vector of 0 of length n. And we try to compute for any random x, the distance, the expectation of the squared Euclidean distance. And this tells us, well, you have an expectation of the square distance to be of order n, which is large if n is large, okay? And if you do the same computation for any independent random vector of dimension n, you measure x minus y and to the power of 2 and take the expectation, you have 2n, which basically give a mental image on our right-hand side saying that, well, even in the case of low-dimensional dimension 1, you have concentration around the mean. This is no longer the case in high dimension, okay? Because I remind you that the center or the expectation or the mean is 0, so it's at the origin. And any random vector living in Rn is at a distance of square root of n in expectation from the origin, so it's very far from the origin, and they're spreading out the high-dimensional sphere, and two independent realization, x versus y, they are almost orthogonal because this is of distance square root of n, this is square root of n, and if we measure zero distance, we have just computed it's going to be square root of 2n. Okay, so they are in the high-dimensional case, they are almost orthogonal. So mental image is something like this. They are not concentrating, they are not getting close to their expectation or mean, and they are orthogonal to each other in the high-dimensional case. Okay, so it seems that for random vectors, we have a very different mental image for the low-dimensional setting on our left-hand side and high-dimensional setting on our right-hand side. But those mental images are not really true, because we still have concentration behavior if we measure using some scalar function, just as I described at the very beginning. Okay, so it seems, according to our mental image, that random vectors or, of course, random matrices will not concentrate around some deterministic quantity, for example, their expectation, but their scalar function do. Okay, we should expect some kind of behavior if we measure the random vector of length n through some observation map or scalar observation f that's it's a random vector and outputs something in R, a random variable, then it should have a concentration. Why should this happen? Because we know law of large number and central limit 0. Okay, those tell us that if you take a specific observation function which is a linear one, you do have concentration. Okay, so we expect such kind of thing holds for random vectors and also for random matrices. Okay, random matrices will not concentrate around any deterministic matrix, for example, in a spectral norm sense, but their scalar observations, for example, eigenspectrum or misclassification error rates of neural nets should concentrate, and we only need to compute the expectation using the idea of determinist equivalence. Okay, and this is a formal or informal definition of determinist equivalence. This just tell you that things will going to concentrate, and you only need to find to evaluate the expectation. And if you can do this, we are done. Then what remains to do for us to handle is an entry-wise nonlinearity, okay? And there are in general two regions. Okay, let's consider again, we have some random vector living X living Rn, and we have some scalar functions that's, take in Rn, so X, and output, say, random variable, okay? Then this observation map may act in two different regions. The first is the LLN region, law of large number. So basically, it's going to give us an almost deterministic quantity. Okay, for example, it's just a linear function that's summing up all the entries and normalized by the dimension. Okay, in that case, the distribution function becomes degenerate, and after the application of this observation map function, you get an almost deterministic quantity as n goes to infinity. You get a deterministic quantity. There is another case where your distribution function is non-degenerate, and you still get a random quantity. Okay, this is what I refer to as central limit theorem region. For example, if you're just renormalize everything by square root of n, and as n goes to infinity, you're converging distribution to a standard Gaussian distribution. So you are not going to get a close to deterministic quantity. You are going to get a random variable. And clearly, if we have a nonlinear functions that apply to this f of x in this two different regions, you expect that your nonlinear function have different behavior. Okay. And that's exactly what we're going to talk about. So here we're going to see this example. We have again a random vector x, okay? It has up to scaling ID standard Gaussian entries. And we have another deterministic vector of length 1. And we're going to discuss the two different scaling regions, okay? In the case of, if we just evaluate, we consider the quantity of interest to be x transpose y, and we have some nonlinear function phi applied to x transpose y, then we know we are in the Ln region because this quantity of x transpose y under the assumption of x and y I just described will converge almost surely to 0 as n goes to infinity. So you're almost applying a nonlinear function to a quantity, to a random variable, but it's very close, it's highly concentrated around the deterministic value of 0. However, if you renormalize everything in the central limit theorem region, you're applying the same nonlinear function phi, but to a standard Gaussian random variable. So there are two regions. And we will say that different techniques of linearization needs be applied in these two different regions. The first results, or the first technique we need to use in the law of large number region is easy, because you're almost going to get a deterministic quantity up to some smaller order random fluctuations. So we do Taylor expansion. Okay. So if the function is smooth, and if it's not smooth, there are ways to get around as well. Okay, so that's easy in the Ln region. In the CLT region, you are going to converge in distribution to a Gaussian random variable. So you need to extend a nonlinear function of the standard Gaussian random variable, and there are ways to do this. So the family of orthogonal polynomials, and in the case of Gaussian distribution, it's the family of Hermite polynomials. So you still understand how to linearize and decompose and understand the nonlinear function applied to a standard Gaussian variable. okay? And we introduce the Hermite coefficients of the nonlinear function we are interested in. But the takeaway would be, so depending on different regions, we do different things. And let's go back to the example I mentioned, okay? So now we consider a specific nonlinear function applied to, scalar observations of random vector into different regions, LLN and CLT. And the nonlinear function we're interested in is tangent hyperbolic, okay? And we're going to say that in the LLN region, if we try to linearize this nonlinear tangent hyperbolic function, we're going to get, just the linear function, okay, T. And as a consequence of Taylor extension, okay, because we know that things will concentrate around 0, so we check the value of tangent hyperbolic at 0 is going to give us the value, it's going to give us 0. So we just check which linear function will be 0 at x equal to 0. It's going to be T. So that's it. Okay. And we can also derive its corresponding expectation. It's almost trivial. In the CLT region, you get different linear function because now you're not going to concentrate around the deterministic value of 0. Instead, you're going to converge in distribution to a standard Gaussian. And now we need to check what is the way to match the two functions, the tangent hyperbolic and another linear functions, so that their 0th order Hermite polynomial match with each other. Because that's what we care. Okay, we are looking for things that's another psi of CLT that can mimic the behavior of tangent hyperbolic in the sense that their first order Hermite coefficients match with each other. Okay, and after computation, we say, well, you need to take, this specific value times T. And if we put everything into figures, that's exactly this, okay? Our left-hand side, we have this peak that represents the convergence of law of large numbers. So as dimension goes to infinity, things concentrate around 0. So you only care about the behavior of your nonlinear function, the tangent hyperbolic in blue, around the point of 0. And if you want to linearize, this is going to be the linear function T. Otherwise, if we have a CLT region, okay, it's going to converge in distribution to a standard Gaussian distribution. And we must evaluate the behavior of this tangent hyperbolic blue curve with respect to the shape of the Gaussian, okay? And then it's going to be to give us a different linearization that has a different loop than in the LLN region, okay? So we use different techniques depending on the region, but in general, we know how to handle the nonlinear share as well. Okay, and here's a roadmap of what we're going to describe in terms of application. We already say that the core idea of the whole proposed framework or the whole paper would be propose a high dimensional equivalent. Okay. And in the linear case, we know things will concentrate around the expectation. So we're going to propose your way to compute the expectation of, linear random matrix models. I didn't describe that in detail, but just say the expectation. And if unfortunately, your model is complicated, but have entry-wise nonlinearity, you need to still first perform linearization, and it depends whether you're living in the LLN region or the CLT region, you do different thing. But after the linearization, you obtain some linear equivalent model and just continue as if you are playing with linear model. Okay. So this is a proposed framework, and we try to, using this proposed framework to understand 3 models, okay, linear models, linear least squares, and nonlinear shallow neural networks, just some naive neural network has 2 layers or 1 hidden layers, and extend beyond the case of shallow to get deep neural nets. And we're going to discuss for all the 3 models their behavior of training error. So how good can you memorize the input error? For example, how good can you use a linear model to learn some linear teacher? what is the behavior of test error, for example, whether we can see double descent behavior or not. And we can also, I'm not going to mention that, but if you're interested, we can also discuss the behavior of learning dynamic. For example, if you run gradient descent on linear model, nonlinear model, or deep neural nets, we can use the proposed technique to give a full picture of the gradient descent dynamic as well. Now let's step into the first application, the simplest one of linear least squares, and the focus would be apply what we have seen, the idea of determinist equivalent, things we don't have nonlinear here, and to understand the behavior of classical region where you have a lot of samples where the data dimension is small. Okay, you are playing with 2 or 3 dimensional data, versus the so-called proportional region where things are both large. Okay, you are playing with high dimensional data and you have a lot of them. Okay, here is a setup. Okay, so we have some input data that are having IED entries, sub-Gaussian entries, for example. The input data are of dimension P, and we have again n of them. Okay, and those are the input data, and the corresponding target, the true ground truths, yi, are generated just by a noisy linear model. Okay, so the corresponding yi is equal to the inner product of the xi against some ground truth parameter beta star plus some independent noise. Okay, so this is a noisy linear teacher model, and we care about. Okay, for this model, we care about its behavior. So for data generated from this model, we care about the behavior of linear squares or linear ridge regression. And we care about 2 quantities. The first would be the in-sample prediction risk, just the training error, okay? Or the out-of-sample prediction risk, just the test error, okay? This R in and R out for ridge regression or simply linear least squares, okay? And for data generated from this model, we want to characterize their behavior. And if we care about standard ridge regression, we have an explicit solution and their equivalent. And these 2 solutions are in fact equivalent for any regression strength gamma strictly bigger than 0. And in the case of linear least squares, we remove the ridge regression. You have the pseudo inverse, okay, denoted beta 0. Okay, and we want to understand the behavior, the statistical behavior of beta 0 or beta gamma for data drawn from this noisy linear model. And in 2 different regions, one in this classical region where n goes to infinity, but p fixed, and in the modern region where NP diverge to infinity together. Okay. And we have the following result. So this is the first result in the classical region where we understand the R in, the in-sample risk or the training risk, and the out, which is a test error. Okay, we have an explicit solution that's going to tell us everything depends on the dimension ratio, the strength of the beta star and sigma square, which is in fact is not a signal to noise ratio, and the regulation term. And in the proportional region, so if NP goes to infinity together, you have a different formula. Okay, it's given by this, differentiation of the Pelges form obtained from Mashinko-Bastard equation. I'm not going to and get into the detail, but essentially you obtain everything if you're plugging the deterministic equivalent framework that we just described a few slides ago. Okay, you get the following. And we feel that they have very different shapes in the classical region if you consider n goes to infinity for p fixed, or if you consider they are both large. Okay. And we have such illustration. Okay. So on our left-hand side, we compare the behavior of training error or in-sample risk. And we compare the behavior of of the in-sample risk with gamma, the regression strength equal to 0, or a little bit regression strength. Okay, and we consider this dimension NP to be, fairly non-zero, something between, for example, 1/2 and 10. Okay, and we plot all the markers in blue circles or red triangles are empirical results. So we run the behavior of linearly squares, on a given finite sample p equal to 500 and n, larger than that, depending on the ratio. We run the empirical behavior and to get these markers, and the dashed lines are obtained from our theoretical prediction. So we see a pretty good match for this in-sample risk, and we can in fact predict this slope using a theoretical formula as well. Okay. Our right-hand side is the behavior for test error, and we see a double descent curve. Okay. For the markers are obtained from empirical results. You really run the model and test on an independent test set. And the dashed line are obtained from the, a little bit ugly, but theoretical formulas obtained from random matrix theory and the deterministic equivalent framework. And we see they match each other pretty well. And you may have double descent curve. That means when n, p are close, the ratio between n, p are close to 1, you may have a peak of your test error if you don't put any regulation. And this peak will, decrease and even vanish if you put a very good value of regulation stress. And the black curve, which is a monotonic decreasing function, is the prediction in the classical region. So if you assume that n is much larger than p, your test curve should be a monotonic decreasing function, but in practice, you never observe that if your n and p are both large. Okay, so there is a gap. And it's always much clearer to use the high-dimensional proportional region to predict what's happening. Okay. As a consequence, I kind of predict what's happening, the scaling law of training error. Okay, we can get very explicit formulas of scaling laws. In this case, we know that for p or the training error will decrease if you don't put any regression strings. Then your training error will decrease just like p over n. Sorry, n over p over n. And we also get double descent and test error in this proportional region that we never see in the classical region. Okay. So that's the easiest thing if we do least squares, just to show that things actually work out, using the proposed framework, and that you observe totally different thing if you're working in the classical versus proportional region. Okay. Then we move on to go slightly beyond that. We work on the shallow neural network model. And this is the model we want to play with. We again have input vectors leaving RP, and we're going to have some first layer weights that are possibly random. Okay, so linear transformation through this first layer width. And then we have some entry-wise nonlinearity that's applied. So this phi function. And we're going to get this random feature model, in fact, phi of wxi. And we're interested in the corresponding training error for this model and the corresponding test error if we have, test on some independent data set. Okay. And we want to understand how things are happening for this model. And first, for deterministic input data, but for random with w as a function of your nonlinear activation function. Okay. And again, this first layer is random, and the second layer, so the output weights will be learned again using, minimize this rich regularized mean square error. So it's given again some beta gamma that's just look like linear ridge regression solutions, but now the features or the random matrix, the original sample price matrix are replaced by some nonlinear random matrix. It's phi that is defined using the product of Wx and through some entry-wise activation function, okay? And we want to understand its behavior, okay? And what one can easily check that its behavior, the training mean square error, the test mean square error of this beta gamma only depend on this resorbent of this nonlinear gram matrix. And we know it's going to again have some deterministic equivalent, okay, for random W and deterministic X. We know depending on difference, as long as your activation function is Lipschitz, we know that it has a deterministic equivalent that tells us how everything evolves as your function, as a function on dimension ratio, and your nonlinear function that will tell the phi that will determine this kernel function or kernel matrix K that will come into play in this nonlinear resorbent. Okay, so this is a deterministic equivalent part that tells us things will concentrate around this Q bar. Okay, and once we have this Q bar, we plug in this formula, we get the training MSE, and we can similarly get the test MSE as well. So we can discuss a lot of things as long as we have this Q bar. For example, we know that we can, depending on the behavior of this Q bar and the nonlinear function, we know we get different scaling laws in the case of shallow neural nets. For example, if we assume that, so everything now depends on the nonlinear activation function, which will determine the eigenvalue decay of the kernel matrix, the K that's appear in our resorbent Q, okay? If we use some cosine activation function, people have derived in the literature, it will lead to exponential eigendecay, and this will tell us an explicit training error that scales like log n over n. Otherwise, if we use some ReLU activation, people have derived this, it's corresponding to Martin kernel, and we will have a faster rate that is of order n to the order of -1 minus beta for some beta strictly positive, okay, which is faster than the rate of 1 over n in the linear case. And we also can understand when this double descent for test error happens, or whether it's not happening. Okay. And these are simulation results. For training MSE and test MSE, all markers are our empirical results, and our dashed line are our theoretical results given by our deterministic equivalent, but for nonlinear one. And it is remarkable that all the numerical results are obtained on real data, because now we are playing with randomness of W. We don't make any assumption on the data X. Okay, so they are run on some handwritten digit data. Okay, but we are still not happy because we want to have a precise understanding of what is the role of activation function, of nonlinear activation function. So we want to go beyond the deterministic equivalent to get some linear equivalent to understand what is the role played by the nonlinearity. So we go beyond to perform some high-dimensional linearization of the kernel matrix, because we know that the nonlinear activation function will act on the kernel matrix that will act on the deterministic equivalent. So we only need to study the kernel matrix. Okay. So in this case, we need to slightly, make an additional assumption that we assume the data vectors are no longer deterministic, but randomly and independently drawn from the unit sphere. Okay, we make statistical assumptions on the data, and in that case, this allows us to linearize the kernel matrix to get the following linear equivalence. And this again agrees with previous results, as we have some linear shift, rescaled linear matrix model X transpose X plus some higher order terms. Okay. And this holds in the case that for any Lipschitz function, you compare the Lipschitz function applied to these two kernel matrices, you're going to get essentially the same thing. So we understand this behavior and the impact of all this nonlinear activation function is going to impact all the via all these Hermite coefficients, this A50, A51, A52, and the nu here. And those are just the Hermite coefficients of our activation function. So we understand precisely what's the role played by the nonlinear activation. Okay. And we want to go even beyond that to understand how deep will comes into play. And so here will be the deep neural network model that we care about. It's a neural network model of depth L, and we do this recursively. We perform linear transformations and then entry-wise nonlinear T, and again linear and nonlinear, etc. Okay, and we now first consider all the weights are random, so all the W1 to WL are random, and we may have different activation function applied in each layer of the neural net. And we similarly define the feature, just like in the case of shallow neural nets, the feature obtained after Lth layer of the network. Okay, you perform linear and then nonlinear transformations for L times, and you obtain this big sigma L matrix. Okay, and we're going to, just as in the case of linear equivalent that I have done in the case of shallow neural nets, we just consider the corresponding kernel. Okay. We're going to study the expectation of the sigma transpose sigma matrix that tells us what is the kernel behavior after L times your neural nets, L layer of your neural nets. Okay, and this, in fact, if you consider the practical, the case where your neural nets are very wide, then all its behavior will be determined by this kernel, conjugate kernel matrix, and you just need to study this. However, if you're not extremely wide, I mean, there are correction terms, and in general, your neural net performance diverge a little bit from this kernel behavior. But now let's just focus on this. And we have a similar results on this, conjugate kernel for deep neural network, and similar results of high dimensional linearization, in the sense that for a given neural network of any depth, okay, finite depth, we can derive a linear equivalent model for the corresponding kernel. And this, pretty much like in the case of shallow, it's just going to be a rescaling of the linear part plus some additional terms. Just all the coefficients are not merely the naive Hermite coefficients of your activation function, because now you have a lot of layers. So all the coefficients that determines your matrix will depend recursively on the coefficients of your previous layer, but still through their Hermite coefficients. So basically, you give me a neural nets that contain a lot of activation function in each layer, and I just need to compute all the Hermite coefficients in all the layers and run this recursive equation to get the behavior of the kernel in each layer. Okay. And we have this, so it will have a pretty interesting behavior in the sense that, so if we make a few assumptions on all the activations in each layer, for example, we assume them to be the same one, then we say a kind of curse of depth, in the sense that if you use the same activation for each layer and you use a very deep neural network, then you are going to get a representation or the kernel matrix that's basically going to be identity. So all these alpha terms that's in front of your input data will vanish as the number of layer goes to infinity. Okay, so it's kind of curse of depth in the sense that if you have unstructured input because now we assume that your data are uniformly distributed in a sphere, then eventually at the very depth you are going to get something, a kernel matrix close to identity. You're not going to extract features using this neural network. However, that only holds if you're, because now we're playing with input data that's unstructured, and we normalize our activation functions, and we don't train with there are counterexamples that if you start with structure input, you assume that you have Gaussian mixture, so more than one class, for example, then we don't see this curse of depth, but a blessing of depth in the sense that we can show if you use 3-layer neural network, then the coefficients that we derive all this alpha here, okay, will be more flexible if you use a 3-layer neural nets than the 2-layer. So you can separate better the Gaussian mixture if you use a deeper neural nets than a 2-layer nets. But if you're no structure, you don't see that. Okay. And things we start with everything's random. Okay, we always want to involve the training procedure. This can be done using some neural tangent kernel idea because the conjugate kernel we just derived has a very close connection to neural tangent kernel. And the neural tangent kernel is pretty nice in the sense that if you're using, sufficiently wide neural nets with trained with, gradient descent with very small step size, then if you understand your neural tangent kernel at random initialization, you understand everything. You understand the generalization and convergence property of your neural nets. Okay, so we basically apply the same thing as we just described, but to get results for neural tangent kernel. It's going to, again, take the same form, but with a different recursion to determine the coefficient for each layer. So we done the same thing for NTK, and it has a very interesting application because we now have a good understanding of the nonlinearity of our neural nets. So we can just change the activation of a given neural nets by something else, but keep the coefficients unchanged. Okay. So for example, to have some numerical advantage, we just put the activation functions to be very sparse or quantized. This allows us to compute less, to accelerate and to reduce the storage of our neural nets. But since we have a theory that tells us if you play this carefully, your conjugate kernel or your neural tangent kernel will remain unchanged. So it means that the performance of your neural network will remain unchanged approximately. So we apply this idea to to perform compression of neural nets, and they work pretty well to reduce memory without hurting the performance. And that's basically everything I would like to share. So just takeaway before I end. So the whole point is to propose a unified framework. And the only takeaway would be the high dimensional equivalence that has 2 parts, deterministic equivalence and linear equivalent, to handle the randomness and the nonlinearity. Okay? I didn't describe the details, but the tools are ready. You just do plugin of the results, and you get results for the model of interest. And with this ideas, we can get training and testing performance guarantee for some naive models, and also understand this training behavior that I described during my talk. And this allows us to do a little bit applications, for example, compression of neural nets. Okay. And that's the references I'm relying on, and mostly are describing this. First references is the overview paper this year. And at the very end, I also do a publication of, advertisement for the book I written with my PhD advisor, Huazhong, where we basically, putting together a lot of things using idea of random matrix theory applied to, different kind of machine learning and algorithms ranging from unsupervised to semi-supervised, fully supervised, and even neural nets, things like that. So we have a PDF version of the book, and all the code to reproduce figures in the book are ready online. And thank you for your time and attention.